Good evening, students. Today's session we are going to explore about the continuous control mode. So under continuous control mode, we have a proportional control, integral control, derivative control, and also we have a composite control modes. Okay. So today's session we are going to explore about the continuous and composite control modes. Okay. So first one is a proportional control. Okay. So what is a proportional control? From the word itself, it is very clear that the output is proportional to the input signal. Okay, so always it is very clear that the output is nothing but your control signal and your input is a error signal. Okay, so error is nothing but it is y of t minus o set point minus a measured variable. Okay, so for the proportional control, the control signal is proportional to the error signal. P of t is proportional to, it is proportional to k kc into u of t, and you have an additional term p bar, that is nothing but the bias. Okay, so p of t is proportional to u of t, and you have that proportionality is replaced by a constant p bar plus kc into u of t, where kc is a controller gain. Okay, and p bar is a bias of the control signal. Okay, so coming to this next one is a integral control. Okay, so in this proportional control, kc should be a positive value. Okay, so next is the integral control. So based from the word itself, it is very clear that the control output depends on the integral of error signal over time. Okay, so p of t is proportional to the integral of e of t dt, and that integration is replaced by a constant which is tau I, which is an integral time constant. Okay, it is also called as a reset time. Okay, it is also called as a reset time or floating time. And next is a integral control. Integral control is widely used because it provides an important practical advantage, because it is eliminating the offset. If we take a proportional control, there will be always the offset is there. To reduce the offset, we go for the integral control. Okay, and last one is the derivative control. Okay, so here you can see that proportional control, the integral control cannot be used alone, and it is always used in conjunction with the proportional control. So already you know very well, you have kc into u of t plus 1 by tau I into integral u of t dt, and to arrive the transfer function, you will get p of s by u of s is nothing but kc into 1 plus 1 by tau I of s. And similarly, if you take a derivative control, it is going to, so a proportional control is going to see the present error, integral control the past error, and if you take a derivative control, it is going to see the future behavior of the error signal by considering the rate of change. Okay, you call that as an anticipatory control or pre-act or rate action. Pre-act. Okay, so that is called the derivative control. If you see a derivative control, it is proportional to derivative of error signal d by dt of e of t, and that derivative proportionality is replaced by a constant tau suffix t, where tau d is a derivative time. Okay, so the control output is equal to the nominal value. Okay, so if you see, the derivative control cannot be used alone, hence it is combined with the proportional control. So you will have kc into 1 plus tau d into s. Okay, so here this is called proportional plus derivative control. Okay, so here it is going to experience the anticipatory strategy is experienced, the experienced operator can incorporate in the automatic controller by using a control output proportional to the rate of change of error signal. Okay, and next is a okay, so you can see that proportional plus integral control or proportional plus derivative control. Okay, so wherever s is there, replace that by j omega, so you will get kc into 1 plus 1 by tau I into j omega. Okay, and similarly for the proportional plus derivative control, you have the same category. So this you have a different forms of PID controller, or say parallel form of PID controller, series form of PID controller. Okay, so if you take a parallel form of PID controller, you will have GC of S is equal to, you will have both the proportional plus integral plus proportional plus derivative, or you have a simplified version of the proportional plus derivative control, integral plus derivative control, which is Kc into 1 plus 1 by tau is plus tau ds. Or if you take a series PID controller, you will have a proportional plus integral term, and along with that you will have the derivative term alone, that is the transfer function of PI and PD controllers, because the transfer function is physically unrealizable. okay, because you cannot this is physically unrealizable, because you can see that the degree of the numerator polynomial is greater than the degree of the denominator polynomial, and so the practical version includes a derivative filter. Okay, so the derivative filter will be in this form. Okay, so you will have this parallel form of PID in this form. So you will have Kc into 1 plus 1 by tau is plus tau ds. Okay, and this is a block diagram representing the parallel form of PID controller without derivative filter. And if you see the series form of PID controller, you will have Kc into tau is plus 1 plus divided by tau is into the derivative filter, that is tau ds plus 1 divided by alpha tau ds plus 1. This is a derivative filter. Okay, so in order to make a system physically realizable, and expanded form of PID controller, you will have Kc into u of t plus Ki into integral. This is Ki is nothing but Kc divided by tau I is represented as Ki, that is integral time constant, and Kc into tau d is represented as a derivative time constant, that is Kd. Okay, so instead of Kc tau I tau d, you use a three element as a gain, that is Kc, Ki and Kd. So these are called as a expanded form of PID controller. Okay, and if you choose a controller, you have to see what is the selection criteria for controller. Okay, so the very important selection criteria is you should have a minimum overshoot and quarter decay ratio. Okay, so that is very important. Okay, and everything you have to give some quantity or a single number, you call that as a figure of merit, which provides always the quantitative measure whether the design controller is good or not. Okay, so that is called figure of merit. Okay, so here the figure of merit provides a means of keeping a score for a different controller parameter, and low score generally wins. And it is dangerous to have a however, to rely solely on the score to determine the best choice of controller settings. Okay, so you have a three important criteria for choosing a good control. One is called integral square error, another one is called integral absolute error, and the last one is integral time weighted absolute error. Okay, so here integral square error is nothing but integral of square of error, absolute error is integral of absolute of error, and integral time multiplied absolute error is integral over 0 to t into u of t dt. Okay, so each of this represents a figure of merit. Okay, and if you see this ISC that has a large value, which usually occur at the beginning of the response because the error is square, and ITAE will penalize the response that has a error that persists for a long time, and IAE will be less severe in penalizing the response for a long error and treat all the errors in a uniform manner. So the ISC is often used in the optimal control theory because it is more easily in a mathematical operation. Okay, so these are the figure of merit, and this is very important to choose the selection criteria for a different controllers. Thank you, students.